All right, so let's talk first about second midterm exam. Right, so I sent many announcements. I did everything that you guys asked for. Like you want to postpone the exam, we postpone the exam. Like you tell me that you have other exams, you never think about postponing other exams. It's always my exam, but that's fine. Do whatever you want, but all I want you to do is just do your best. Study for the exam. So all what we are gonna have in the exam, these topics, chapter 14, work and energy, right? But you have to have the basics, because sometimes in the work and the energy, you have to find the velocity or have to find the distance. Maybe the whole problem is not about the distance or the velocity, but you have to have the basics of how to find the time from velocity and distance, or distance and acceleration. So you have to have this background. Number 2 is going to be on chapter 15, impulse and momentum. Alright? And number 3 is going to be 1 questions on fluid dynamics. Alright? So there will be 3 questions, maybe 2 work and energy and 1 impulse and momentum, maybe 2 impulse and momentum and 1 work and energy. So it's gonna be like 4 questions. Try to cover these 3 things and think about them like this. Work and energy was like the kinetic energy 1 plus the potential energy 1 is equal to the kinetic energy 2 plus the potential energy 2. It has 1 rule. This rule is half mv1 squared plus mgh plus half ks1 squared is equal to half mv2 squared plus mgh2 plus half ks2 squared. What is this? This is the energy at stage 1 and energy at stage 1. Like you have a body attached to a spring, and this spring is compressed and it's at elevation from the datum, this elevation, and then this body came here. Okay, just giving you a random example. So what happened? This body has an initial velocity here and final velocity here. Has an initial elevation here and final elevation here. And this spring was compressed with initial compression, and it has a final compression here. So you put the initial stage here and the final stage here. So here is the initial kinetic energy, initial potential energy, initial strain energy, final kinetic energy, final potential energy. That is the general rule for all this chapter. Okay? So, and for, if you guys remember the impulse and momentum, it has the integration of the force, F dt, plus mv1 is equal to mv2, right? So the impulse plus the initial momentum equal to the final momentum. And we had a bunch of impacts, and we have the restitution coefficients, and all this stuff. I believe there are going to be only 5 equations that you need to master and know what is each one of these values is. If you know them and you read the problem very well and translate the word problem into numbers, like when we say starting from rest, that means that the velocity is equal to 0. And then you define the datum. If you define the datum here, so the initial height is 0. But if you define the datum at the final one, so the final one is 0. And you know that anything above the datum is positive, below the datum is negative. So try to train yourself. Put the rules in front of you and solve 1 or 2 problems by yourself and see if you can solve them using these rules or not. Okay? I'm not going to give you hard problems, but the thing is, you get even the easy problems, but you don't know how to start solving. Or even, I want you definitely to get the final answer right. But if you didn't get the final answer right, that's fine. But show me that you are doing the steps, that you understand the sequence, that you understand the process, and you substitute in them. Actually, anyone who did this in the last exam, he got almost the full mark, the whole points, even if he didn't get the final answer right. Okay? Same thing with this chapter. For the fluid dynamics chapter, you know what you have got in this chapter. I don't even know what did you got here. So try to focus on what Professor Leon told you in this chapter. Okay. All right. Does that sounds good? Fair enough. Okay. So this lecture of today, should I keep this, everyone? Okay. Today's lecture, I believe, to be honest, it is the most important lecture for you as a structural engineer. Why? I told you before, what do structural engineers do? You guys took any structure analysis class? Structure analysis 1? No? How many got structure analysis class? All right, so that's fine. So, is any of you try at some point to be a structural engineer or continue as a structural engineer? Environmental? None of you environmental engineer? So who's else? Like, what other than structural engineering? Like environmental, transportation? What, is there any other? But civil is like the big umbrella. What classes, elective that you are gonna pick in the civil engineering? Like, are you gonna pick more concrete classes, steel, transportation, environmental? All right, so whatever, actually the process is the same. I'm gonna match it when you pick to be an infrastructure engineer. As a structural engineers, what we do is, when we design buildings or when we design structures, we want to make sure about two things. What are these two things? We want to make sure that the structure is safe and has what we call the minimum amount of serviceability. What is this? What does that mean? Safe, that means if this is structure under our load, it doesn't fail. That's number one. We don't want this structure to fail. So if you have a column, like let's say if you have a beam. Oh yeah, I forgot to put a name for this lecture. So this lecture is gonna be, and actually this is not in the textbook, okay? It's called Structural Dynamics. So all what we have done so far, it's called particle dynamics. Okay, so that's the part that we have done before the fluid. And then Dr. Leon gave the fluid dynamics part, and then I was supposed to give today the rigid body dynamics, but maybe I'm gonna use these two lectures before the midterm to tackle this part, the structural dynamics part, okay? Structural dynamics part is a really huge discipline, and I'm gonna give you just a little bit of summary about it. Like, maybe you need to take 1 or 2 classes to cover all the concepts in this part, in the structural dynamics part, okay? But what I'm doing right now today in this lecture, just a summary of what structural dynamics do. Thing is, this course is different from the one in the mechanical engineering. They focus only on the particle and the rigid body. Here we are making it more dynamics of engineering systems like particles, fluids, structural, rigid bodies. So we take multiple of them. All right, so that's number one. So, but before I start the structural dynamics, I want to tell you what is the mission of structural engineers, what they are supposed to do. You guys all taken trusses like in the statics, right? So you have a truss system like this, something maybe like that. Or you have a beam system, that's a beam, like this. That's all the structural system. As a structural engineers, we want to make sure that these systems, when they get loads, external loads, like if you have a load like this, or a load like this on this beam will not fail. Like it's not gonna not gonna crack here, and this truss is not gonna fail. That's number one. But let's say it's not gonna fail, but I want also when I use this in my system, like if I use this for my floor system here, when I walk, I feel comfortable. Like I don't want it to like go up and down with me. Sometimes some floors, they are very flexible. So when you walk, you feel like vibration. So that's what we call serviceability. So they need them to have an allowable deflection. Like when they deflect, like this deflection delta, or this deflection here, to be within the allowable. okay? And what is the allowable, that what the standards is doing. So maybe when we design a structure actually, like let's say I'm designing a floor system and this is my beam, and I designed the beam, I got the reinforcement in the beam, I got the cross section of the beam. That's what we do as engineers. Like when we design, like when we put loads, B, in concrete design, you design this section, that means you get what is the cross section of this beam. Like let's say this beam is 0.7 meter by 0.3 meter. That's the cross section of the concrete. And then you find the reinforcement of the concrete, like how many steel bars that we are gonna have here, based on the bending moment. So it's a complete course, reinforced concrete, to find what cross section and what is the reinforcement. Let's say we take the reinforced concrete class and we're able to find the cross section that is gonna resist this load and it's not gonna fail. That's number one. Number two, you are gonna check the deflection, how much deflection you are gonna have here with this cross section. Well, let me ask you, if this cross section is bigger, what is gonna happen to the deflection? It's gonna be more or less? Like let's say, if I put bigger, then what does this section need? You are gonna have less deflection, right? Because it's gonna be more stiff. But let's say I put a small cross section, what is gonna happen? It's gonna be more deflection because the cross section is less stiff, all right? But let's say I found this cross section is the cross section is needed to resist this load, and it can be by the code. But when I found the deflection, and I checked the deflection by the code, it was delta was less than the delta minimum that the code is given to me. So what should I do? You have to use the minimum. You have to increase the thickness, all right? So that's rule number two. So when we design building, we design them on two things. We design them for resistance, that we have to have the capacity to resist the load, and the serviceability to have the minimum amount of displacement as required by the code. That's for any structure. Same thing with lateral loads. That's vertical loads. We call them gravity loads because they go to the gravity. But when you have an earthquake, and that's the topic of today, structural dynamics. So when you have an earthquake and you have a building, and this building, the foundation is shaking from down, and the building is making like this. So you also still want to have, like let's say an earthquake is hitting LA, and there's a building that is 60-story, and it's gonna shake. Well, I want this building, when it shakes with the earthquake, it doesn't fail, like there's no cracks or anything, and in the same time, I wanna feel comfortable, like I want to be like, not be dragging all the way. So maybe when we design the building and we get the cross section, we found out that this cross sections is not gonna fail, but I'm gonna have deflection 3 meters. This building goes 3 meters that way and 3 meters that way. No, this is not allowed. So I have to increase the cross sections to minimize maybe to 0.5 meters, right? Or usually in tall buildings, like if you have been to like 60 or 100-story buildings, like in the top story, the allowed deflection is high. Sometimes it goes to 0.7 meters, like the building is making like this all the time from the wind. So sometimes it gets uncomfortable. So some owners, they say, no, I want to increase the cross sections. I don't want to have this. I want to minimize the deflection of the building. So we knew as a structural engineers that we need to find the resistance. We need to design the cross sections to make our system safe. And we need to find the deflection that is going to make the building comfortable to stay in. All right. But I'm saying comfortable, I mean in the regular loads. Like don't like jump on the floor and then make it vibrate and say it's not comfortable, okay? So because you are putting an extreme load on the building that is not designed for it. Okay, so our job in, I can erase that, right? Our job from a structural dynamics is, I have, for example, a tall building like this. Has multiple stories. And this tall building got exposed to an earthquake, like something, we usually represent the earthquake with something like this. this is the time, and this is what we call ground acceleration, and it is something like this, something like that. That's how the earthquake look like. What does that mean? That's my building, and that's my foundation. That's the ground acceleration over time. The ground acceleration, that means that the ground is moving with an acceleration and it's shaking, and then it's shaking very, very slow, and then at some point the acceleration increase and then decrease again, and there's some aftershock, and then decrease again until it dies. Okay, so that is the ground acceleration, right? So that is the input. So you have an earthquake somewhere. Let's say that this is the ground and the source of the earthquake is here. Like, I don't know, a fault in the rocks or a San Andreas thing, or something here is gonna happen. And when this thing rupture or this thing happen, the earthquake is gonna happen. And once it propagates in the soil, let's say in through the city, every part of the city is gonna have different response. Maybe all the city is gonna be exposed to the same earthquake, but every building is gonna have different response. Why? Because every building is built differently. The wood, the concrete, the steel. So that's how it is, right? So, and then when it comes to this building, this is the ground acceleration of the earthquake. And mostly, every earthquake have its own ground acceleration. Like there's a well-known earthquake that happened in California. It's called El Centro. So you have an earthquake and it have its own ground motion. We call this is the ground motion. All right? But the thing is, we want to say before, do you remember? We have a load B and we put it in a beam to get the delta. Right now, B is not constant. B is like an acceleration, and basically it's a ground acceleration. When you multiply with the mass of the building, you are gonna multiply mass by acceleration. Is gonna give you the force on the building. And the force on the building is not constant. Like it starts slow, like it's basically like a force hitting the foundation here. And this building is gonna shake with a force F, which is equal to mass multiplied by acceleration of the earthquake. And then this force was like small, and then hit big in this direction, and then in the other direction, and it goes until it dies out. You guys understand this? Is everything clear? All right. So that's my load. So I want to apply the earthquake load on my building and find what is the delta of my building, the same way that I did here. I want to put load B on a beam, and I want to find what is the final delta that I have. This building is going to have a maximum deformation, something like this. The slabs at the top stories is going to go at a high displacement. The one in the lower stories at a low displacement, because the building is going like this. So the maximum displacement is at the top elevation, and this one is going to have something like this. So this is story. And I want to find this delta. The delta on the top story, because this is the allowable delta that we are looking for. We want to make sure, after we design this building, that this delta is within the allowable. And usually for high stories, delta allowable is the height of the building over from 400 to 600. Like let's say that our building is 600 meter height, so you divide 600 meter over 600, and then it's gonna be 1 meter. That's the allowable displacement at the top story. Some people want to go to the lower, like use divide over 400. That's also one way to do it. But we want to stay within the allowable, all right? The thing is, how we can find this delta? We need to use the structural dynamics to do this. That's why we are gonna discuss today structural dynamics. Do you guys know what we are gonna do today? We need to find this delta. All right, so to do this, I need to start with something first before dive deep into structural dynamics. The thing is, what resists the earthquake here is the columns, okay? So usually, when we design building, we have a gravity load resistance system and lateral load resistance system. The gravity load resistance system is the floor system. Like our loads, live load, us, dead loads is the carpet, whatever, the flooring and everything, that's called dead load. What resists this dead load is the beams Like if there's a beam between this column and another column here, that's resist load locally. Like this system has nothing to do with the slab from over there. It's locally at this floor. Take our load. But what is the global system is the columns, because the columns take the loads from all the upper stories down to all the stories down there. Like let's say this column is taking the load from the story above us and the story above us and all the stories. But this slab only takes our load. Doesn't contribute to the loads from the upper stories or the lower stories. So let's say, how's the load getting distributed? Like let's say we are here in this story, our load get to the beams and from the beams to the slabs and go to the columns, and the columns go to this column, this column, this column, all the way down until it gets to the foundation, to the piles, and from the piles to the soil. So this is how we transfer all our loads from here to here. The thing is, when we think about any system, we need to transfer the loads to the soil, okay? So if you have a bridge, you have to transfer all the loads from the bridge to the columns, from the columns to the foundation. So if you are here, your load is gonna be distributed in this state, and then this column is gonna take it all the way down to the foundation, all right? So that's what we have as a load. So the system that resists the loads here is just the beams and the slab. But the system that resists the lateral load is the columns, and sometimes in some buildings, we put big columns. Like let's say if I look at this plan, I cut here and I look down, you are gonna find something like this. You are gonna find some columns like this, small columns, and you are gonna find an elevator, and there's a reinforced concrete core around this elevator, something like this. This core is a really stiff element in the middle of the building and make it much more resistance to the lateral load. Sometimes this core is not enough, so we put maybe some shear walls, like long columns here, all right? Or some long columns here. So when you see this big columns, what we call shear walls, that means that this building, that this element is gonna resist lateral loads. All the cores, like here there's an elevator or something, and usually around the elevator they put cores. This core is just for lateral loads. Definitely takes gravity loads, but also it's a stiff element. Think about it as like, this is the floor system, like this. And you have some columns, and when the earthquake happens, it's gonna make like this. But let's say you put a very stiff element here, like a shear wall of concrete that is very long here. When you got hit with an earthquake, this system is gonna make like this because there's a very stiff element holding it from here. But the thing is, this is not good. We don't want the building to have torsion. Torsion is really bad load. Why? Because it squeezes the column, and it makes shear, and makes moment, it makes a lot of, you don't want to design your elements for torsion unless you need to. So we try to avoid as much torsion as we can. So we want to try to add maybe another element here so my building doesn't make torsion and make it like move that way. I want my building to move that way, not to make that way. Or you put a core in the middle so the building can shape that way. So that's a very stiff element that makes the building resist lateral loads. All right, so you have your lateral load resisting system, which is the columns, all right? The thing is, I can solve this building as is with 3D. It's really difficult for engineers to do this. I need to find a way that I can group all these buildings in one group and make all of them as a one column. So I want to simplify this building. So to simplify this building, so if I know the stiffness of this column and the stiffness of this column and all the columns in the versus story, I can make all of them here. This is a story number 1, 2, 3, 4. All right. So right now I'm trying to condense the system or simplify the system so I can solve it because this building is huge to solve. So I get all these columns. Let's say this is stiffness K1, K2 up to Kn. Let's say K1, K2, K3 up to Kn. You get the sum of the Ks. And by the way, the sum maybe is not absolute summation. We're gonna find how we can get the total K. Like let's say not sum, the K total. For story 1, K total for story 2, K total for story 3, whatever, up to K total for story n. So right now I simplified the 3D building, and we call this multi-degree of freedom system. Like you simplify also the mass, you take all this story mass, like from here to here, and you got all these masses, and you put them as a single mass. And this story as a single mass, and this is story as a single mass, and you put all the masses, like from mass M1, M2, M3 up to Mn. So this is the first simplification. So I simplified from 3D multi-degree of freedom to a 2D multi-degree of freedom. That's the first simplification, all right? Actually, I can further simplify this system into one big mass and one big column, like this, and have K total. How? By finding the stiffness here and the stiffness here, and find a way to sum them and make them in one big column and one big mass. But to make sure that your summation or your simplification is right, this building is going to give you delta under this load. It's supposed if you did this simplification right, if you put the same earthquake weight on this building, it should give you the same delta here. And if you did the same load here, it should give you the same delta here. If it gives you different delta, that means your simplification is wrong. Okay? Why we do this? So that we can solve this system in a simple way, because it's impossible that we can do it as a whole building. Actually, if you get a beam, you might solve it wrong. Like if I give you a load on this, you might solve this wrong. So how about if you solve it this one, or solve it this one? It's gonna be very complicated. So how we can do the simplification, or how can I sum these stiffnesses? I'm gonna tell you how we can do it right now. So let's assume that we have a spring and let's say 3 springs. And these 3 springs are in parallel and attach it to the wall, and there's an element here, and this element is very stiff and can move uniformly. Like when you apply a load on this beam B, all these springs are gonna move either this way or either this way, depends on the load direction, all right? We call this springs in parallel. Right? So let's say that you apply the load B on a spring that has a stiffness K1, and this spring has a stiffness K2, and this spring has a stiffness K3. So when you pull this, all these springs are gonna move together, right? They all are gonna have the same delta, right? Because this, once it moves, this spring is gonna move delta and delta and delta. What is gonna happen? Each one is gonna get different load. Like this one is gonna take B1, B2, and B3. So, but at the end, the final load B is gonna be equal to B1 plus B2 plus B3. That is how's the final load. The thing is, there's 3 loads here or 3 springs here, and you are pulling this one, so everyone is gonna take a part of this load based on its stiffness. Okay? All right. So do you guys remember Hooke's law? We had that has B is equal to K multiplied by delta. Do you guys remember? Okay? So the thing is, the final delta multiplied by B, since we have here B's, okay, we can leave this right now, and also I can put this equation like when you say, I can say that the delta, this is gonna have delta 1, and this is gonna have delta 2, and this is gonna have delta 3. By the way, this stuff is not in the note. Maybe I will upload it in a separate note, or I rewrite it after the class. So just try to make sure that you take all these notes. All right, so from this I can say that delta is equal to delta 1 is equal to delta 2, and it's equal to delta 3. They all have the same delta, right? That's what we got from here. Because the thing is, when you pull this from the middle and it's gonna move uniformly, it's not gonna make different delta at each one of them. We either move together or we are not gonna move, okay? All right, so let's get back to this equation. Since you know that B is equal to K multiplied by delta, so this one is gonna be equal to the K total multiplied by the delta total. And this is gonna be equal to B1, and B1 is gonna be equal to K1 multiplied by delta 1 plus K2 multiplied by delta 2 plus K3 multiplied by delta 3, right? The thing is, we already know that delta is equal to delta 1, equal to delta 2, equal to delta 3, so all these are equal. So you can divide by delta, so all these are gonna be gone. So basically, if you wanna find the K total of these springs, you sum them, the sum of all K's, K1 plus K2 plus K3. So you can actually, if this is 1,000 and this is 2,000 and this is 3, so you can say that these are equivalent to one spring that has 6,000 tons per meter. And if you put B equal to this B, this is gonna give you the same delta that you are gonna have here. Did you got this? So if you have a system of springs and the springs are in parallel and you apply B, you can basically get the K total equal to the sum of all the K's. Does anybody have any questions so far? Okay, let's talk about the springs in series. You have springs in series. By the way, the springs means like maybe you have a bar. Like I can have a bar here and a bar here and a bar here, and they are attached to the wall, and there's a beam here, and you can pull this beam with the 3 bars. When we put springs, the springs is the model of the bar. This is the axial stiffness of the bar. Okay. Same thing if I have springs in parallel. Like if you have springs in parallel, it's gonna be something, spring number 1, and then a spring number 2, and then a spring number 3. And then you have something here, and you are gonna pull with a force B like this. Each one of these springs has a stiffness. Let's say this is stiffness K1, K2, K3. By the way, this system in real life, let's say that this is the stiffest element and this is the lowest stiffness. It's something like a bar that has different dimension, like a bar that has this size, and then this size, and then this size. This is the most stiff, less stiff, and less stiff. And you have a force here on this system, something like this. That's the actual system. All right, what is the special about this? The special about this system, here, all the springs have the same delta, but here, all the springs have the same force. Like the resistance here is B, that's the reaction. And the thing is, if you cut this section to get the normal force, it has B. If you cut here, it has B. If you cut here, it has B. So B here is equal to B here is equal to B here. Like let's say that we have a bunch of wires and we connected these wires together. One of them is thick, one of them is less thickness, and we try to pull them. All of them has the same normal force, but everyone is gonna have different delta, like based on its stiffness. Like let's say when you pull this, I believe that this one is gonna have less delta because it's very stiff, have delta 1. This one may be a little bit bigger delta, delta 2. This one much bigger delta, delta 3 because it's less stiffness, all right? But at the total here, this point is gonna move delta equal to delta 1 plus delta 2 plus delta 3. The delta that happened here plus the delta that happened here and the delta that happened here. So, since you know that delta total, and by the way, I told you that here is gonna, all of them are gonna have the same B. Like here, let's say this is gonna have B1, and this is gonna have B2, and this is gonna have B3. I can say that B is equal to B1 equal to B2 equal to B3. But delta is equal to delta 1 plus delta 2 plus delta 3. Actually, it's the opposite of this one. Here, B is equal to B1 plus B2 plus B3, but delta is the one that is equal. Here, it's reversed. So, I can use also here Hooke's law, so I can say, since we know that B equal to K multiplied by delta, so I can say that delta is equal B over K. So, here, B total over K total is going to be equal to B1 over K1 plus P2 over K2 plus P3 over K3. And since I know that all the B's are equal, I can divide on them. So all these B's are going to be gone. So I'm going to have 1 over K total equal to 1 over K1 plus 1 over K2 plus 1 over K3. Alright? So that is the rule that we have here. Okay, so you guys know how to get the total stiffness if the springs are in parallel or the springs are in series. By the way, the building systems are the same thing. Like, let's say that this is my building. And I have a bunch of columns here. How can I know if the columns are in series or in parallel? And when we talk here, we talk about, here there was axial stiffness. But the thing is, the way that columns work, it works with the shear stiffness, because the loads go this way, and the load makes shear on the column this way. But you can think about it the same thing. Like, let's say that this column has a shear stiffness something like this, like a spring like this. Right? And all the columns are like this. And when you push the columns, all these springs are going to resist the loads. Like, think about it that way. But let me ask you here, I'm going to put this building in here. This building, when it gets an earthquake that hit the base, something like this, F base, and it's going to have a deformation. Look at this. Can you see this delta? The delta at story number 1. Assuming that the slab is a really, really stiff element. Very, very stiff element. It's the most stiffness element in the floor. Tell me, what is the displacement that this column is going to make at this point? This delta, right? And this one, this delta, because the slab takes all the column together, this way or this way. None of the column can leave. None of the column cannot say, oh, I'm not coming. So we all coming together or going back together. So we all have the same delta. Look at this. Here, they all have the same delta. So what do you think? All these columns are in series or in parallel?
Parallel.
Better, like this, because they all have the same delta. This column, and this column, and this column, so they all have to have the same delta, like this, because this slab is going to move from here to here and take all of them together. But this is under the consideration. I don't want to take you talk about it right now. We assume that the slab is a rigid diaphragm or rigid slab. Some slabs are not rigid. Some slabs has many holes for the stairs and HVAC, and it's not that rigid that take all the columns together. We call it flexible slab. But let's assume that the slab is rigid and it's taking all the columns together and all of them has the same delta. So basically, if I told you that this building has 4 columns, and each column has a stiffness of 100. So the total stiffness of all these columns is going to be the summation of 1, 2, 3, 100 plus 100 plus 100 plus 100, 400. Okay, so direct summation of all these stiffnesses. But look at this. What is going to happen at the other slab? The thing is, the other slab start from the slab below, like start from here, and then go all the way here. Because the thing is, if story number 1 move, story number 2 has to move. Okay, and then it's going to start from the movement from story number 1. So it takes the delta 1 here and move another delta. The thing is, these columns did 2 movements. There is a movement that we call translation and rotation, right? I don't have any problem with a story to make a translation, because the translation doesn't make any bending moment on the column. Like if I say that this building moved like this as it is, that's why some technologies right now, it's called base isolation. They do it for the earthquake. When an earthquake happens, the building make like this as a 1 unit. So they isolate the base and it moves like this. This is really healthy movement. As soon as the building is not having differential translation that can make bending moment and crack the section, that's really good. If my building is moving like this, that's really good. But if my building is making like this, the columns might break. Okay, so that's a problem. So this columns make a translation and goes here because of the movement of the story number 1, and then make the rotation. So that's delta number 2. And same thing with the story number 3. Make delta number 3, delta number 4, until it goes to the last stories. Most of the deformation happen in the lower stories. The upper stories is like a little bit of deformation. But the final delta that happened up there, what about it? It's actually delta 1 plus delta 2 plus delta 3 plus delta 4 up to the final delta U plus all the delta. What is this similar to? Look at this. This is delta equal to delta 1 plus delta 2 plus delta. So this system as a stories are in parallel or in series? In series. So the columns here are in parallel, but if you want to sum them with other stories, that's in series. So this system do the first simplification. So this system is going to be the first simplification. It's going to be a bunch of masses like this. And let's say this is K1, K2, K3, up to Kn. And here's mass 1, mass 2, up to mass n. You guys remember K1 is going to be equal to, because they are all in parallel, so it's going to be the summation of all the K's here. Right? And this is going to be summation of all the K's in this story. But if you want to sum this story and this story and this story to make this is going to be in series, this rule. You take 1 over K total is going to be equal 1 over K1 plus 1 over K2 plus 1 over K3. And if you want to find out this is going to be, you guys know, you have to make this like K1, K2, K3, and then the thing is you are going to make all of them like this, and then you are going to have here K2 plus K3, or K2 multiplied by K3 plus K1 multiplied by K3 over K1, K2, K3 plus K1, K2 over K1, K2, K3. So I make, below I make it all of them K1, K2, 3. And if you divide these two by this, K2 and K3 are going to be gone and you're going to end up with K1. Same thing here. And then it's going to be equal to this plus, and then the top is going to have this plus this plus this. Anyway, there's a way that I can calculate this thing and find the K total. So I showed you right now, how can I transfer from a 3D building that has multiple columns in the 3D and sum all of them to get this system and get this system. This system, as I told you, it's called multi-degree of freedom system. And this system is called single degree of freedom system. Alright? Okay, so next step is, I want to solve the single degree of system, but before I solve it, I showed you how I can sum the stiffnesses. The thing is, there's another important parameter that contributes to the building resistance against earthquake. It's called damping. So, as you know, if we have an earthquake hitting a building, we need a very stiff element to resist this element. But there's a component that dissipates the energy of the earthquake. It's called damping. When an earthquake happens, sometimes we put in our buildings, I'm not sure if you guys see, like a piston, that like when an earthquake happens, something that open and close to dissipate the earthquake energy. Some buildings, if you guys watch some YouTube videos about Taipei building, they put like big tanks, like a very circular pole filled with water, and when an earthquake pushed the building that way, the tank goes to the other way, and the building got that way, the tank goes to the other way. So that's another way. Every tank on top of a building, tank of waters, they act as a damping system. All right. Even when you have a connection between a column and a beam, and this connection is open and closed, it dissipates the energy of the earthquake in a heat and friction. So we call this damping too. It has the same parameters, like we can actually, when we represent it, like we have the stiffness, summation of K, and we put another system like this, like the piston, that we represent it with the summation of C, and C means the damping of all the building, okay? But anyway, don't think about it. Let's focus on the stiffness. I'm just giving you information for the future when you take advanced class. So we put also the damping coefficient. And as we know, if we want to get force from a stiffness, we multiply the stiffness by delta, K by delta, right? Like if we want to convert the resistance, like if you have a system has a resistance K, B, the force is equal to K multiplied by delta. And if you have a system has a resistance of C, the damping coefficient C, the B is equal to C multiplied by the velocity of the system. That's the resistance of the system, okay? So, let me write this here. Okay, so right now, I have a system, has a mass M, and has a stiffness K, and has damping C, and this is the base. That's my system. And let's say this system got exposed to an earthquake, and this earthquake is something ground acceleration, and this is the time, and this earthquake is something like this, and it's gonna generate a force at the base that's equal F base. Actually, it's not constant, it's function in time, because every time step, keep it changing. My target right now, my goal is to solve this system under this load. How can I do this? Let's imagine a dynamic problem. You have, I'm gonna put the free body diagram. This is my mass, and I'm gonna put it on wheels because my mass is gonna move. And this is the mass of the building, by the way, the mass of all the slabs and everything. And this mass is attached to a spring, and also attached to a damper. Damper, I told you, it's like something that is allowed to dissipate the energy. Here and here, and the damper has a coefficient C, and the stiffness of the building is K. And somehow this building, under some force, Ft that comes from the earthquake. By the way, it can come from the wind, it can come from a blast, whatever. That's a general problem. And we call this a single degree of freedom problem. All right, I want to solve this problem using the dynamic concept. Okay, let's say under this force, this building at rest it was here, and then under this force is gonna move, right? It's gonna move that way. You guys remember when we take the summation of fx is equal to ma, or max, and that is the direction x. So let's put all the forces in the x direction. Thing is, once this mass is moving that way, you are gonna have a force here, resistance, and a force here, resistance, right? It's gonna resist. Thing is, you wanna hold this that way, there is a damper is pulling you, and there's a stiffness of the column is pulling you back. And the force here, if K is equal to K multiplied by delta, and this one is, and by the way, we can remove delta and we say Ku, the distance. Because if this moved distance U, so it's gonna be K multiplied by U. And here I told you that C is function of velocity, so the force Fc is equal to C multiplied by V, the velocity of this mass, if you want to find the force in this damper. So the forces that I have here, the positive one is Ft. I'm going to assume that the positive is this direction. So I'm going to have Ft all right? That's positive. What is negative? Fk is negative K multiplied by U, and this is negative C multiplied by V. By the way, I can remove V and put U dot. Like this. Because V is the time derivative of the distance. Okay? And all this is going to be equal to M multiplied by AX. The acceleration, right? That's the left side. So the acceleration of this body is going to be the summation of these things. And I can remove AX and I put U double dot because the acceleration is the second derivative of the displacement. Well, I can rearrange this equation. When I rearrange this equation, I'm going to write it over there so that everyone can see it. I'm going to send this to the other side. So I'm going to have the mass M multiplied by U double dot plus C multiplied by U dot plus K multiplied by U will be equal to Ft. I remember this equation for years. I never forget about it because that is the basics of structural dynamics. This equation. Without this equation, you cannot solve the structure. Okay, so by the way, you guys solved equations like this in math. Have you seen equations like this? I'm not saying the same equations. You have seen equations that has U dot, U whatever. Do you guys remember what it's called? Differential equations. Have you guys done this in math? Differential equations? What is the difference between the regular equations and the differential equations? Regular equations are like U squared plus U plus 2 equal to 0. Solve the equation and find U. That is a second degree equation that is direct and you can solve it by finding the value like U. Do you guys remember? It was plus and minus, whatever the numbers here, right? This one is not the same. This one is differential equation because it's function in derivatives. And by the way, do you guys remember homogeneous and non-homogeneous equations? So if this value is 0, like the factor here is 0, it's going to be homogeneous equation. But this one is not homogeneous. I can put this 0, so it's going to be homogeneous. So this is, and by the way, what is the degree of this differential equation? Second degree, why? Because we have a second derivative here. So that's a second degree partial differential equation, all right? And this is, as I said, it is the most important equation when it comes to structural dynamics. All right. If I solve this equation, what is the output from this equation? Like when you solve differential equations, what do you want to find out? Solving equation, you want to find the variable, right? So if I solve this equation, what is the variable is? U. I want to find the value of U, right? Solving this equation is the same thing. I want to find the value of U. And by the way, what is the value of U? It's the displacement of the structure. That's what we want to find out. We want to find out how much delta U that the structure has. So if you solve this differential equation, you will be able to find the value of the delta. I'm gonna put the equation here again. So we have M U double dot plus CU dot plus KU is equal to F KU. I'm not gonna solve the equation here right now because it's gonna take needs one lecture. I'm not gonna test you how to solve it, but you need to memorize it. So we're gonna have a final exam and it's gonna be something about this lecture. Okay? I'm not gonna ask you to solve anything in this concept. I just wanna make sure that you understand the concept. I will ask you, show me how does the multi-degree freedom look like. So you wanna show me something like this, something like this, and something like this. Show me how you can simplify a building from a 3D to a multi-degree freedom to a single degree freedom. You have to show me all these. Show you masses, you have to show stiffnesses, you have to show how you sum the stiffnesses. If I ask you to show me what is the differential equation of the building, so it's gonna be this equation, and I want you, for example, sometimes to show me something like this, all right? We call this the resisting function. We call this the forcing function. Why? The thing is, this force is going to be resisted by the mass of the building, the damping that the building has at the stiffness of the building. And this is the force that applies. So, that's what we have. Okay, let's say the way actually to solve this is really, really hard. Why? Because the force is not a constant value. If the force is constant or it's zero or something, maybe it's easy to do it. Not easy, still, like you have to spend maybe an hour to solve. You guys know how solving differential equation look like. You did it before. So, but the thing is, our forcing function is something like this. See? The thing is, you have to divide this curve into small pieces and take each small piece and integrate your solution over the time series of the whole thing. So it's a completely different level of mass to do it. But the thing is, once you solve this thing, you are going to have the value of u, and that's actually what we are looking for, the value of u. Okay, let's say somehow you were able to do it. And by the way, when you get the value of u, you are going to get multiple values. Why? The thing is, when the force is small, what do you expect the value of u to be? Small. But once you hit the peak of the earthquake wave, so the value is going to be big, and then the earthquake is going to die again. So once you solve, this is time t, and this is the earthquake, AG. Let me put it here. Something. This is AG, and this is T, and this is the earthquake, how it looks like. When you put this as an input for this equation, you are going to get an output like this. This is u, and this is time t, and it's going to be something like this. You are going to find out that the displacement is going to be something like this. All right? But I'm only interested in the maximum displacement because this is going to develop the maximum deformation and the maximum internal forces inside the car. I'm not interested in the small u's, I'm interested in the maximum one. Now let me tell you something. If this earthquake hit a city that has thousands of buildings, do you think that all the buildings are going to have the same U? Why? It's the same earthquake. Same earthquake hit a specific city. So, do you expect that all the buildings are going to have the same deformation? Okay, I need like a good reason. Why no? Different material, what else? Different heights, different locations, different soils. Even if you have two buildings are constructed like the same, like you went to a community that have the same models. But by the way, the construction material maybe has not the same properties when you poured concrete here and poured concrete here. Maybe the soil under these buildings are different. So everyone is gonna have different response, okay? So that's one thing that you should know about the buildings, that every building is gonna have completely different response. And this is gonna take us to something that's called the natural frequency of the buildings. Every building has its own fingerprint based on its stiffness and mass and damping. these three parameters, M, C, and K. Every building has different mass, different stiffness, and different damping. These three parameters. That's what makes the solution is unique for every building. So, like our system, this system here, is gonna have T natural frequency. What is the natural frequency is? The natural frequency is the time that the building make like this and go like this and come back to its original place. Make one cycle to come back to its original place, right? So it has a rule, it's called, but we are gonna assume right now that this doesn't exist, that the building doesn't have damping so that we don't complicate things. So T is equal to something is called like 2 pi over omega. And that makes sense, like if you have a circle like this, and you start from here and you cut the distance 2 pi and you divide them by the angular velocity, you get the time. Okay, it's like distance over velocity is gonna give you time. The natural period or the period of the building to make one cycle is the 2 pi over the angular velocity. So, and the omega is equal to, that is the new thing, omega is equal to the square root of K over M. That is a general rule. The omega of a building, omega is the frequency of a building, the angular velocity of the building, it is equal to the root, the stiffness over the mass. So if you want to find T of any building, it is basically 2 pi multiplied by root the mass over the stiffness. That is the general rule of the natural period of the building. And we call the natural period of the building is the fingerprint of the building. So any building has its own natural period based on its mass and its stiffness. Now let me ask you, if you have two buildings, one of them has a stiffness K equal to 100 and one is 1,000, which one is going to have natural period that is higher? If you have this number is big, like the stiffness is really huge, it's going to make T small. Why? Because your building is small, so when it gets hit, it returns back to its original place. But if it's flexible, it's going to make like this. So the stiffness is a small, and once the stiffness is a small, this number is going to be big. Same thing for the mass. If you have a small mass on the top, the building is not going to make a lot of movement. If you have a big mass, the mass is going to be thrown away. So the more the mass, the more the T. Okay, so that's T. So, all right. So right now we knew that every building is going to have different mass, different stiffness, and it's going to give you different response. We call this a response. So this response is called displacement response, and you can actually get U dot velocity response, and you can get U double dot, which is the acceleration response. So they are going to be something like this, and then the acceleration is going to be something whatever like this. So that is the responses of the building. All right? Okay, so next time I'm going to talk about something that's called responsive vector, but I want to tell you one last thing about the natural period of the building, T. The thing is, say I have a building like this. The thing is, this period, the T time T, because since I explained the T, I have to explain this. The natural frequency or the natural period of the building, when we say the period of the building, it depends on how the building is going to move. So when we say T is equal to 2 seconds, that means the time that the building needs to go this way and go this way, that movement, and come back to its original position. But what if it's going to make movement in the other direction? It's going to be completely different T. What if the building is going to make different movement? In tall buildings, they don't move like this. Sometimes they move like that, like they dance, like this, like a bark is going that way and a bark is going that way. So it depends on the movement. That's why we call that buildings have moon shapes. Okay, and some buildings actually, when it comes to really, really tall buildings, sometimes they make like this. You cannot see it, but it's there and it's a small. So they make like a dancing waves. But the thing is, the buildings have all the mood shapes at the same time. Like the building, like let's say I have my building has, this is the most and easiest mood shape that the building can do. It goes that way, and that's having a short building. They go that way. But if you have more tall buildings, you might see something like this, and or this, or this, or this. The thing is, you will never see this. This is very, very small that you can see it. The thing is, buildings already have all these node shapes are together, but with different contribution. Like maybe 90% or 80% of the movement of the building is this one, but this one maybe 5%, and this one is like 2%, 0.01%, and this one is like 0.001%. So buildings have all these node shapes are together, but with different contribution.
Is there any time that the buildings oscillate without earthquakes?
Well, you have to have, well, there's something that we call natural vibration. That's the one that without any earthquakes. It's like, that's the oscillation of the building without any external loads. And that's like the mode shape, this mode shape doesn't depend on the loads. Like these mode shapes is just for the buildings. Like what is the natural movement of the building? When the loads apply on the building, that's what decides the contribution of each one of these. Depends on how the load look like. But all these are natural modes of the building. Like let's say that you build a building small, so you will find that these mode shapes, the higher mode shapes doesn't show up, and this is the one that shows up. So there is something called natural modes, and then there's the vibration happen, it's going to be contribution of these loads. And this contribution depends on the external loads, how they look like. Like let's say you applied a very, very high load on a very, very tall building, so maybe this load is going to show up with much more participation. And that's going to take us to something called the participation mass ratio. How we can know the contribution of each one of these loads, we get something, we see how much of the mass was moving with that shape and how much of the mass was moving with that shape, and we find the contribution of each one of these nodes. And by the way, when we design buildings, we look at the participation mass ratios. That's a very, very important criteria. Don't want to get into details, but when we design buildings, the codes say that the various node shape need to oscillate or need to vibrate at least 90% of the mass. Sometimes you have to include. The thing is, the more node shapes that you are going to include, your software is going to run more analysis. Maybe it's going to take forever to run for the higher node shape. So sometimes we cut the node shape until 10. But until 10, we only find that node shapes that oscillate 80% of the mass. That means at the end of the day, I want to find the 100% of the mass. How do you not only 80%? Okay, so I don't want to get you in more details, but it's good that you know for now that the building has some node shapes. And node shape number one is the dominant one, and the other one is the higher node. So for now, that's it. Next time we're going to see how we are going to use this concept in something called responsive spectrum, which is the basic, as a structural engineer, any structural engineer should know this concept, right? Get prepared for the second midterm, because this is the second shot to improve your grades. And let me know if you have any questions, send me your email. I have some exam sheets from midterm number 1, if you want to pick it up from my office. See you guys next time. Let me turn off the